session on aerospace and new mobility. And let me introduce our first speaker, Kheng-Lim Ko, Associate Professor of Newcastle University in Singapore. And he's also an author of Discontinuous Fiber Reinforced Composites, Fundamentals of Stress Transfer and Fracture Mechanics. And his topic for the session is Uncompleted Repair of Damaged Fiber Composites, Prospects and Challenges. Ladies and gentlemen, please join me in welcoming him. Hello, Mr. Go. If you're ready, you can start your presentation.
Thank you very much for a very generous introduction. Many thanks to all of you for attending this session. Okay, I would like to begin by sharing the screen first. And here we go. Okay, so today I'm going to talk to you about composite repair, about what we are doing right now with composite repair, its prospects and challenges. I work for Newcastle University in Singapore in a research institute as shown here. And for the composite repair, I actually collaborate with the Republic Poly in Singapore and with my colleagues in Newcastle University in UK. For this topic on composite repair today, there are 4 areas that I'll be covering. I'll be taking you through about the motivation of why we want to do composite repair and where we are now in terms of the state of the art, and then what we have developed as I'll be showing you in composite repair and the challenges and prospects. So, carbon fiber reinforced composite laminate, as we now know, is widely adopted in many engineering applications, particularly for making primary structures. And we know that these covers many industry from renewable sectors. We have the wind energy as discussed in earlier talks just now. And we also have in the transportation in sectors, the aircraft industry, and also in the EV vehicles. Now, I just want to give you a sense of what could happen as we all know that these industries are going to grow in the next in the next couple of years. They're going to grow very rapidly, and we will be seeing more of these. So it might just be that if any of these encounter damage, and if they are not and if we don't do something about them, like repairing them, for instance, or they might end up in the landfill, they might end up with a catastrophic environmental issue. So we need to do something right now to think about what could happen in future. Obviously, there's a lot of talk about recycling of the composite material, and we heard about that in previous talks yesterday. But there are also hurdles to recycling due to the technology. For instance, the mechanical properties does degrade with each cycle. If we choose to repair, and if we have to do effective repair, we need to understand what the business in the industry expects from repair. And we also need to understand what the technical department in each of these industries expect. So we know that they are looking for restoring mechanical properties to pristine condition, requiring little or zero wastage of good materials, fast turnover time. Repair can be done internally in the garage or in the field, and also repairing, make sure that it's robust. Now, ideally, of course, if we want to deal with effective repair, we might just have to go back to the drawing board to design for repairability, like for instance, subdividing the parts into smaller parts, the structures into smaller parts. But of course, this might not be practical. In 2012, together with Professor Jeff Gibson at Newcastle University, we started the composite repair program in Singapore. And since then, we have been looking extensively into damage, characterization of composites, and also designing a wide suite of composite repair devices. Now, to see what we are trying to repair, let us just very briefly go back to some fundamentals about composite fiber reinforced, continuous fiber reinforced composites. So as we now know, if when a composite material is loaded externally, and in order for the fiber to be able to take up the load, there has to be good interaction between the fiber and the matrix at the interface. And these depend on several factors like the fiber matrix properties, fiber surface, bonding, and the mode of stress transfer at the interface. Now, under extreme loading and leading to catastrophic rupture of the composite material, now in the process of this, then there's a lot of things going on. And first, maybe the matrix may crack or the fiber pull outs from cracked matrix areas, or even fiber fragmenting. So what we are trying to solve, and this is our overall goal, is to try and repair these features. But on a modest scale, we might just have to deal with just some of these features that we can repair. Okay, and we find that for the problem we want to deal with, it fits very well with some of the damage, like for instance, damage arising from low velocity impact, like as simple as a tool drop or even a knock. And what we find that these leads to barely visible damage. As the name suggests, it's barely visible to the naked eye in most cases. And you can see this at close up, showing the indentation due to the damage, due to the impact. But very often, it's what we don't see at the rear part. And that's where the crack line can occur. And these can occur in very inaccessible, and this can be very inaccessible to us, these rear areas. And we know what will happen if we don't nip in the bud, because there's a likelihood that the crack could propagate and leads to catastrophic failure. So what we know is all repairs, like the composite repair, such as the conventional step patch repair process, require very skilled technician. And there's a lot of steps that goes into it, from excavating the damaged material around the structure to putting in fresh materials to patch it up. There are a couple of good advantages for doing this, but also a couple of bad disadvantages, like high wastage of material, and you need very experienced technician. The classic self-healing concept would be something ideal if we want to do away with the conventional repair method, because this is really a step change approach. But of course, there are also limitations to what the self-healing concept can do, and I'll be happy to discuss this at another session. We found that there is an alternative to trying to repair damage, like barely visible damage. Instead of using the conventional method, we could use the resin-injection method. And this is relatively straightforward, involve drilling closed holes if that's the minimum, then one hole is for the resin to be injected into the crack area, and another hole is which is known as the vent hole, is for flushing out debris, moisture, and what have you. Now, the advantage is it's inexpensive. There's very little material removed compared to the conventional method. The disadvantage is because we are talking about drilling holes, good fibers could be broken, and also resin injected may not completely infuse into the crack. What we understand from resin injection method, and in order to carry out an effective repair, this cover three areas. We have to deal with the injection device, we have to deal with the preparation process, and the resin as sealants for the repair. And all these would involve issues like how to draw out the dirt and moisture from the cracks effectively, how to mitigate or compensate for damage due to holes drilled, and how to enhance the resin infusion into the crack. And to deal with these three areas, there's also three so-called ingredients involved. And these three ingredients, which I'll be taking you through in the next couple of slides as to how we actually use them as parameters for understanding resin injection repair and developing a resin injection device that is useful, is first and foremost the pressure difference between the injection pressure and in the non-injected zone in the crack, for instance, and then the effective delamination length for which the resin flows through the crack, and finally the resin viscosity. So the first area for dealing with resin injection repair is the resin injection device, and we want to achieve high pressure. Well, also because as the ingredients suggest that if you have high pressure, you could also have shorter time for the resin injection repair process to take place. And of course, that's good because it contributes to shorter turnaround time for the repair. And for resin injection device, we take our motivation from the simple windshield repair injector that you find in a typical car garage. We find that this approach has been also adopted in earlier studies since 2010 and until quite recently. But we find that most of these prototypes that are reported in the literature are relatively not very straightforward to operate, and also bulky, and therefore not portable, particularly if you want to really think about bringing it into the field for repair. So what we did was, after several iterations of design and looking at seeing if we can improve on the existing repair system, we finally come out with what we have here as shown, a portable, lightweight device that also can be mounted not just on flat surfaces, but also on curved surfaces. And it also have vacuum ports to control the pressure to achieve high differential pressure. So, but of course, developing the device is one thing. We also have to look at the processes that goes into the repair. So we want to also achieve a small effective length for the resin to flow, because that contributes also to shorter time for repair, for the resin injection repair process. And this involves trying to make up for the, for instance, how many vent holes should we be drilling, and what's the distance between the vent hole and the resin injection holes. And we find that, as we all know, when you do drilling, you end up with local damage around the hole. And so we have to ensure that we have a way to do this very well, and also very straightforward. And we also explore how many vent holes needed. We find that in the literature that there's a lot of studies ranging from 4 holes to 5 holes and 6 holes. But the results, the repair efficiency results has been rather contentious in that, that there's no real trend as to what's the best number of holes. It could range from, the repair efficiency could range from as low as 47% to even as high as 126%. So we carry out extensive study to try and understand how many holes and what's the how does the number of holes affect the mechanical property of the damaged laminate when you drill these holes into the damaged laminate. And so that enables us to optimize for the number of holes. We also looked at how the look at developing resin for the healing healing process. So our goal is to want to have low resin viscosity, obviously, or it can flow much better through the cracks, but also it contributes to shorter repair time as well. But we also want to see if clearly epoxy is used in the repair if the most times if the for instance if the matrix is made from epoxy, then you use epoxy resin. But we also want to know if we can also enhance the typical resin like epoxy, for instance, enhancing it by looking at enhancing strength when it's cured. So we looked at how we can blend the epoxy with nanoparticles, because we know that blending nanoparticles into epoxy and when it's hardened will actually enhance the mechanical properties. And we have looked at nanotubes of halosides and carbon nanotubes. And we explore how when we blend these these nanoparticles into the resin, we looked at the wettability of these resin in order to establish the best concentration of the nanoparticles that we should be using for each of these types. And we also looked at the strength of these resin when cured using the lab shear tests. So with all these findings, then we move on to see how we can do the repair of damaged composite, and how good is the mechanical property of the repaired composite under normal service loads and under extreme loading, of course, is what we are interested in. And we found, and we did this for 2 types of laminate plies, the 16 and the 24 ply. And we find to our delight that for the repair efficiency with regard to stiffness, fracture strength, fracture toughness, very good for 16 ply, reaching as close to pristine condition. However, with increasing thickness of the laminate, like the 24 ply, we find that the repair efficiency is not too good. And we are still looking at trying to see what we can do to optimize this so that we can achieve higher repair efficiency. So to summarize, this schematic shows how we carry out our repair study to look at repairing barely visible impact damage composite from how we achieve reproducible barely visible impact damage to looking at how understanding the fracture morphologies and also the repair of the composite material. So here are three simple key messages for to wrap up my talk. We know that CFRP laminates are susceptible to impact damage, or the mechanical properties can be severely degraded by this damage. And we have introduced a new straightforward resin injection device and the process for repairing barely visible impact damage. Like to welcome collaboration or to apply the resin injection system to other areas like recycled composite or natural fiber or non-planar composite laminate and etc. etc. And I welcome suggestions from the audience. And to wrap this all up, moving forward, if we do see the resin injection process and device taking going forward into the future, here are just two snapshots for today. Is we do anticipate that then there will be smart drone to search for these defects, and also with regard to the device, we would probably see a smart robotic arm as also discussed in previous talk about robotic arms and in this case for repairing the damage. So many thanks to my collaborators and thank you for listening.
Thank you very much, Mr. Ko. And can I check if there is any question or comment for your presentation in on-site? 혹시 네, 질문이 있으시다면 마이크 전달드리겠습니다. Yes, we do have a question for you.
통역 부탁드립니다. 저기 현재 항공 사업 쪽에서
I'm in the aerospace industry, we use the injection method,
인젝션을 사용해서
but we currently do the manual injection.
적용되는지 정확하지 않습니다.
So we don't exactly know how much pressure that we are using. So I want to know what is the level of pressure that you are using
어느 정도 영향을 줄 수 있는지
and how much it can impact the composite. So I want to hear your comment on that.
시내에서의 주입
And generally, so what is the pressure bar that you use usually for resin injection?
Thank you very much. I'm pleased that you asked. What we did with the pressure implementation, we didn't do this. We do this in a very semi-manual process with an injection syringe that is attached to an injector that can control and also monitor the pressure of the syringe as it pumps through. What we use for injection is, and we monitor the pressure in the ambient pressure around it using the hot bonder because we have vacuum ports to attach to it to attach the hot bonder to it, but just for the convenience. So because we also do this in a very manual sense, but what we did was we monitor the pressure internally, and we look at achieving 27 milli Hg for what we are trying to do. So of course that there's always a certain time to achieve this. It wouldn't be instantaneous, but once it hits 27 milli mercury Hg, then we start the repair process. I hope that answers your question. But as to the right amount of pressure that we need to put in, we did this with the help of stepping on the foot, because we developed a foot rest system that can just press it very nicely so that our hands are free to hold and put the device on and then do anything to ensure that should anything happen, our hands are able to arrest the system.
예, 감사합니다. Thanks
Thank
for
you.
your present.
Thank you very much. And is there any further question or comments on site? If not, I'd like to express my sincere gratitude to Mr. Go for your presentation. Thank you very much. 여러분 박수 한번 부탁드리겠습니다. And next, I'd like to introduce